Hello students, today we will know about damped oscillation in a simple harmonic motion executing by a particle or a mass or a system. Damped oscillation in simple harmonic motion. To know about damped oscillation, see here. First consider a system as shown in the figure. A spring is fixed to a rigid support with its one end and its another end is fixed to a mass block. Its mass is capital M. The mass block is connected to a rod and the second portion of the rod is connected to the vane which is submerged into a liquid. A liquid is filled in a container and that container is placed on a surface. Now we will study here the simple harmonic motion or the oscillation for the movement of the spring mass block with respect to its mean position. So here we are going to study for a spring mass block simple harmonic motion. Consider a spring mass system executing simple harmonic motion such that the vane attached to the mass block having mass m through a rod as the motion of spring mass block system is up and down with respect to mean position or the initial position. The vane also moves into the liquid in up and down directions during simple harmonic motion of spring mass system. What will happen here? The liquid will exert a viscous force. The liquid exerts a viscous force against the movement of the vane. Also, a restoring force of spring acts there. Thus, the oscillation of spring mass block system will finally be damped out due to two damping forces acting against simple harmonic motion of the system. Let the net restoring force of the system is denoted by a force which is a function of time. Then it can be put equivalent to Ft equals to minus kx minus bv equals to restoring force in the spring plus the damping force provided by the viscous force of the liquid. Consider this the equation number 1. The spring force is given by Fs equals to minus k x whereas the damping force provided by the liquid will be given by minus bv, where x is the displacement of spring mass system from mean position and k is the spring constant. Similarly here, for the viscous force, the damping force, v is the velocity of wind and b is the coefficient of viscosity. So we can rewrite the equation number 1. Ft will be equals to minus k xt minus b vt. Consider this the equation number. We can express the same equation number 2 in terms of the displacement for all the parameters. For this we can write here the force is m multiplied by acceleration as a function of time minus k xt minus b vt. Again it can be rewritten as m d square x t d square x upon dt equals to minus k x minus b dx upon dt, or m d square x upon dt square plus b dx upon dt plus kx equals to 0. The solution of the above equation number 3 provides description of motion of block under damping force, under impact of damping force. So the solution of equation 3 we achieve here as x t equals to a e to the power minus bt upon 2m cos omega dash t plus phi. Say this the equation number 4, where a is the maximum displacement of the mass block, m from its mean position, and omega dash is equals to square root of k upon m minus b square upon 4m square, which is known as the angular frequency of a spring mass block system under impact of damping forces. And here we know the term K upon M is equals to square of omega naught, where omega naught is expressed as natural angular frequency of system. If the value of coefficient of viscosity equals to V is very small, then omega dash will be equals to square root of K by M, which will be equals to omega naught. So under absence of any damping forces, system will oscillate with its natural frequency. But still, if there are some air friction and other damping forces, the oscillations will be finally damped out and the system oscillation or simple harmonic motion of the system will be stopped. So that's all our discussion regarding damped oscillation in a simple harmonic motion. We will continue in the next topic. Till then, good day.